This basically concludes our discussion of the DC motor. And we'll just summarize a few limitations of this implementation of a DC motor. One is that there's quite a bit of friction and wear between the brushes and the commutator. You can imagine these brushes constantly rubbing against the commutator. This creates friction, which hurts the efficiency of the motor, and it can also wear out. You eat away, you wear out the brushes, you lose a connection, and the motors don't work. So the sort of robustness of a DC or a brushed DC motor can be limited. Another issue is the fact that you have this current flowing through this long winding of resistive material. This wire generates heat, and since that heat is trapped in the center of the motor, it's difficult for it to escape, and this can cause problems with the motor being damaged. This was one of the things I had said previously about not wanting to run the motor at its peak torque for a very long amount of time, because that current that is needed generates heat, which can damage the motor, melt the windings, etc. DC motors can sometimes have limited speed range and limited efficiency, and some of these issues can be addressed with an AC motor. And so subsequently we're going to discuss a few different types of AC motors, more at a conceptual level, just the basis of their operation, without getting too much into the mathematical details. One type of AC motor that's important for electric vehicles is the permanent magnet synchronous motor, or the PM synchronous machine. It's a type of AC motor in the sense that the current through the motor alternates direction. The current alternates, that's what AC stands for, alternating current, as opposed to the DC motor where the current remains in the same direction, direct current. A PM machine is also sometimes called a brushless DC motor. The fact that the frequency of the alternating current must change, that means that the source must be from a DC supply. So it's sometimes called a brushless DC motor because the supply is DC, even though the current itself is changing direction. And the way that the DC supply is changed into alternating current is through the use of an inverter, either to create a sinusoidal or approximate a sinusoidal current, or what we call trapezoidal current. I've seen in some instances that machines where the current is trapezoidal is called a brushless DC, and a machine where the current is sinusoidal is called a synchronous AC machine. Another reason why a PM synchronous machine is called a brushless DC motor is because the speed-torque characteristics of the motor are similar to a brushed DC motor. As I'll show subsequently, the mathematical models for the two types of motor have the same sort of structure. Here's a picture of this type of AC motor, which we can use to better understand how it operates. So the rotor itself is a permanent magnet, and the stator consists of three phases of windings: an A phase, a B phase, and a C phase. The current in each of these phases is approximately sinusoidal or trapezoidal. It's alternating current, and that alternating current is approximated from a DC source, from a battery, using an inverter like this. So by changing the frequency and the order in which these switches are opened and closed, we can approximate alternating current in each of the three phases, which you can see here. So it may not be perfectly sinusoidal, but we can sort of approximate it with small steps. Thinking back to that previous picture, the rotor is a permanent magnet, so the magnetic field is fixed. And this is where part of the name comes from. That's why it's called a permanent magnet machine. And the coils on the stator are energized in sync with the rotor. So that's why it's called a synchronous machine. So looking back on the previous slide, the current through each of these three phases, they're at their peaks at different times. And by doing that, the magnetic field generated by each of the phases moves, interacting with the permanent magnet rotor to sort of pull or push it around the motor. In order to synchronize the energizing of the different coils, we need to be able to sense the motion of the rotor. And that can be accomplished in a number of ways, some of which we've discussed previously, including Hall effect sensors, optical encoders, and maybe most commonly resolvers. And the control of the synchronization is very important to the operation of the motor. This is something we'll talk about a little bit later on in the course. And the fact that there are no brushes, the armature itself is in the stator and it's stationary. So we don't have any need for brushes in order to get electricity to the stator. So there's less worry with the brushes wearing out. And the fact that the armature is on the external part of the motor means that it's easier for heat to escape. And so this solves a couple of the issues we saw with brushed DC motors. That's not to say that PM synchronous machines don't have their own drawbacks. They can be more expensive. They can have issues with safety in that the magnets in the rotor can come loose or become demagnetized if the motor gets too hot. And this type of motor can also sometimes have a limited constant power range. So here again is a picture of this type of motor. The stator field is generated by these three-phase alternating current. And even though in this picture the phases are sort of concentrated in these three locations, in general the windings are distributed around the outside of the motor in order to get better torque properties and reduce cogging. But again, the windings may be distributed either sinusoidally or trapezoidally. When we model an AC machine like this, a three-phase machine like this, we can model each of the circuits individually. So just like with a DC motor, how we had an armature with some lumped resistance and some lumped inductance and a back EMF and all that, we can do the same thing for each of these three phases. Alternatively, we can represent the three phases all together all at once as a single rotating current space vector. And this won't be entirely clear from this picture, but there's an animation on the next slide. The current through each phase is changing sinusoidally, so getting larger and smaller, becoming negative and then positive. So each of these three phases are alternating at different times. If we sum all three of the phases, all three of the sinusoidal currents, we get a vector whose amplitude is constant but whose direction is changing as the three phases are energized in succession. And then the control is to maintain the current space vector in a certain location relative to the magnetic field. And thinking back to a cross product, where force is the cross product of current with magnetic field, the force will be greatest when these two vectors are 90 degrees apart. So the control, in order to achieve maximum torque, will keep the space vector I sub s 90 degrees ahead of the rotor, which is generating the magnetic field. Okay. So here's an animation that's sort of showing this concept of a space vector. here's the A phase, and it's alternating. The current through this phase is alternating sinusoidally. So it's negative, and then it's 0, and then it's positive, and it's back to 0. So the phase through this current is alternating sinusoidally. Same thing with the B axis and the C axis. And so when you sum those three together, you get this black vector, which is the space vector I sub s, which has a constant magnitude, but its phase or its direction is changing as these three phases are energized in succession. Here's a picture of a permanent magnet synchronous machine from the first generation hybrid escape. Here is the rotor, which is a permanent magnet rotor. These little squares are the magnets, and just like we saw previously with regular DC motors, we typically have more than just the two poles, more than just one north and one south pole, and that's what's being accomplished here. And here we have the stator, which has three phases. You can see the three connections to the windings representing each of the three phases, and you can also see how the windings are distributed around the outside of the stator, as opposed to being concentrated in three distinct locations. And then here's the larger system, where this large motor is sort of the traction motor for the vehicle, but then there's also a generator, which is also a permanent magnet synchronous machine, but is slightly smaller, and they're connected via a planetary gear set like we talked about earlier in this semester. So briefly, we want to compare the DC motor we spoke about earlier to this brushless DC motor, this permanent magnet synchronous machine. With a DC motor, the magnetic field has a constant direction because it's produced by a stationary magnet. So this magnet with its north pole and this magnet with its south pole are always located in the same direction, in the same location. They're stationary. So B is stationary. And then the current vector is made stationary by commutator action. If there wasn't a commutator, in essence the current would flip back and forth as the rotor turned. But through the use of the commutator, we always are able to keep the current basically pointing in the same direction. With a brushless DC motor, the magnetic field is generated by a permanent magnet rotor, which is spinning. So this magnetic field is moving, and this current space vector I sub s also moves, and it's kept in sync by using a control system. So in essence, the brushless DC motor achieves sort of electrical commutation, where the energizing of the three phases is done in order to try and keep the current space vector 90 degrees ahead of the magnetic field in order to generate the maximum amount of torque. So looking at these are very similar, and we'll show that a little bit further. So the previous example showed the similarity, and it turns out the mathematics are basically have the exact same structure. So the torque itself can be calculated in the same way, where the torque is proportional to the current in the armature, as long as the angle between the current space vector and the magnetic field are kept constant. So if that angle is kept constant, then the relationship between current and torque is also constant, and we have this proportionality constant K, which is the motor torque constant. And the armature in this motor, even though it's static, even though it's part of the stator, it still has the same dynamics in the sense that it still has resistance and inductance because it's a piece of wire that's wound, and it still has a back EMF. In this case, you have a back EMF because you have a conductor in a changing magnetic field due to the rotating rotor, whereas with a regular DC motor, the magnetic field was constant, but the conductor was moving. But in each case, you still generate a back EMF. And the rotor also has the same sort of mechanical dynamics in both motors, because in both cases the rotor has inertia and there's friction. So looking at this, the two types of motors have the exact same mathematical form. This is one of the reasons why a permanent magnet synchronous machine is sometimes called a brushless DC motor. What's different, however, is that sometimes the relative values of the parameters may be different. So here are the dynamic equations representing the permanent magnet synchronous motor, exactly the same as a brushed DC motor. In this case, I sub s is the current space vector. One way in which the parameters tend to be different between the two motors is that with a brushed DC motor, the inductance tends to be relatively small, but with a PM synchronous motor, the resistance tends to be smaller. With a permanent synchronous motor, the friction can also be smaller than with a brushed DC motor. Another type of AC machine is called an induction motor. An induction motor has a similar stator where the armature is stationary on the outside of the motor, three-phase, but the rotor itself is different. So in a PM synchronous machine, the rotor is a permanent magnet, but in an induction motor, the rotor has this sort of form, sometimes called a squirrel cage. And so it's not a magnet, and there's no physical electrical connection to the rotor, but current is induced in the rotor by this conductor being in the presence of a changing magnetic field. And so this current is induced in this squirrel cage, which creates a magnetic field which interacts with the magnetic field from the stator, causing a force which moves the rotor. And in the same way that we were able to analyze permanent synchronous motors, we can either model this on a per phase basis. This is a three-phase motor, so you could have a circuit for each phase with a stator part, the induction of the current into the rotor. So this could be one phase in an induction machine. Or we can model it using the equivalent current space vector, I sub s, where we sum the currents through each of the three phases, phase A, phase B, and phase C. So this brings us to the conclusion of Module 9, where we discussed electromechanical actuators. We first described how solenoids worked, then we discussed DC motors in quite a bit of detail, generating both dynamic models and static models of a DC motor. And then we discussed a couple of important AC machines, the permanent magnet synchronous motor and the induction motor. At more of a conceptual level, we didn't quite get into the same amount of detail. But if you take another course in electrical machines proper, you'll get into the AC machines in much more detail.